All right, our final presenter today is known as Dr. Atiq. He's a professor of computer science at the University of Oklahoma. His research interests are in the area of next-generation computer networks, wireless and mobile networks, satellite networks, switching, and routing. His research program is supported by the National Science Foundation, NASA, and various other highway organizations and agencies. The title of the presentation, Connected Vehicles for Enhanced Driver Safety. Dr. Atiq.
Being the last presenter is always a difficult task. And this one is especially difficult because as a computer science professor, you're sitting between a group of transportation engineers and home. Where is my presentation? Here it is. So my presentation is about cool cars, not cement or pavement or concrete. So it's going to be a difficult one. I know, but so we're talking about smart cars of the future, and I'm going to describe how these cars are going to enhance the safety of drivers. So let's start with some numbers. I think most of you are familiar with these numbers, that vehicle crashes on roads and highways cost life and property and damage to property. This is from 2012, 33,000 deaths, 2 million injuries. The cost is staggering. The cost per person for traffic fatality is 3.2 million, and injury is 68,000. Now you might say, how come it's 3.2 million? I think it takes into account all the losses and the loss of opportunities, all sorts of stuff. The thing is, quarter of these crashes happen during the severe weather conditions. That's what we are trying to focus on in this project. And the weather-related crashes result from a number of things: wet pavements, rainfall, snow, sleet, icy pavement, snow or slushy pavement. So those are the stuff which we're talking about. We're not talking about tornadoes, because these are data taken from DOT and Highway Safety Administration, so they don't worry about tornadoes there. Some quick statistics on weather-related crashes. If you look at the total number of crashes, the weather-related crashes, out of those, the wet pavement are 74%. The rain is these are crashes. 46% of the crashes are due to rain, 17% due to snow, sleet, 12% due to icy pavement, and so on. So these are just some statistics, and these are reliable statistics from DOT. So what have we done in the past to reduce, to increase the safety of drivers? Most of the effort has been primarily on better weather prediction. We alert the drivers that there's bad weather coming up. We have designed better pavements so that cars run smoother. I mean, they're better, and the pavements are better. Also, we have designed schemes to help people survive crashes. Once there's a crash, how can we make people survive the crashes? But if you look at the past effort, there has not been significant effort to avoid crashes by providing the drivers with real-time road weather conditions in the neighborhood. So this is what happens. What normally happens is I want to drive from here to A to B. I look up the weather, and then I travel. But when I'm in a spot, I'm not very aware of the spot in real time. And sometimes I see that there's a car in front which is fishtailing. Then I know that there's an icy spot, right? So that's how I get the information. So if you look at modern cars, these cars are equipped with a lot of sensors, and day by day there are more sensors being introduced in these cars. And these cars measure different operating conditions and the surrounding weather environments. Some of these sensors it can have a location from GPS. We have speed sensors. We have braking intensity sensors, ABS sensors, accelerometers, anti-roll chassis control, infrared thermometers, road traction, etc. So these are all sensors which can actually measure what is happening in the car and its surrounding. And some of these sensors, not all of them, can represent actually the road weather conditions where you are actually. So here's an example of a black ice detection sensor. And this is a project which has been, which was tested in Finland. So let's say there's a car in front which is actually losing traction. And if we could convey this information to the cars behind or the trucks behind somehow, then in real time, we're talking about real time, then it would actually increase the safety of the drivers of the vehicles. So what we need to do in this particular case, as an example, is we need to design a sensor which can detect black ice. Number two, we need to convey that information to the driver. So those are the two things which needs to be done. But the critical thing, it has to be done in real time, instantly within fraction of a second that the car in front is slipping. So what are the possible approaches? How can we convey that information? We can connect all the vehicles wirelessly so that we can route the information from one vehicle to all the vehicles surrounding in the area using wireless. Now, wireless is a sort of developed technology. So the next step would be to connect all these cars using wireless. And then as soon as you have some information which would be useful to drivers in the surrounding area, disseminate the information fast, very fast. We're not talking about uploading information into a database somewhere in the web and then the driver going through his or her cell phone to find that information. We're talking about alerting the driver in the dashboard immediately. So if we can do this, connect all the cars and disseminate the information in real time, then we can, of course, increase the driver safety. This would be additional information to the drivers. So the objective of this sort of work is to enhance the driver safety by enabling the drivers to have a 360-degree awareness of what's happening around the driver and inform of any potential hazards. So the main objective of this project, which has been recently funded by SPTC, thanks to SPTC for the grant, is to reduce the vehicle crashes, fatalities, and injuries. The thrust is on adverse weather conditions. That's what the thrust is, due to adverse weather conditions. So the approach we're going to take is to connect the vehicles in an area using wireless to form an ad hoc network. So it's a mobile ad hoc network. So if you look at the on the picture on the left, so these cars have wireless capability, and when they're on the highways, as soon as they join the highway, is going to connect to all the neighboring cars automatically. So that's a ad hoc network. And it's a mobile because cars are coming in, cars are leaving. So this network of cars, it is ad hoc. It stays there for seconds or minutes, and then it breaks, and the new cars come in. So maintaining a network like this is a challenge. That's where the challenge is, to maintain a mobile ad hoc network which changes so fast. So there are two types of data which can be obtained for connected vehicles. One is we can disseminate the vehicle data, like latitude, longitude, speed, brake status. If a car in front of you is braking, we can actually immediately transmit the information to the neighboring vehicles so that the vehicle following you can immediately figure out that the car ahead is braking. Turn signal, that the car is turning, vehicle length, status, vehicle weight, bumper height, all sorts of information we can transmit to the neighboring vehicles. The other type of information we can actually transmit to vehicles in area is infrastructure data. So these are not safety data or information from the cars. These are infrastructure data like signal phase and timing, speed limits, how many parking spaces are available in the parking lot. Those are infrastructure data. So coming to the connected vehicle applications, there are three major thrusts in this type of applications. One is the safety, second is the mobility, and third is the environment. And within the safety, there are a number of applications. One is to communicate between vehicle to vehicle. Let's see if the laser pointer works. Okay. So the vehicle to vehicle is you are communicating between vehicles, and with that you can actually develop these applications where you can actually avoid forward collision. You can transmit forward collision warning. You can develop applications for emergency electronic brake light, and all those applications you can develop when you are communicating between vehicles. If you are communicating between vehicles to infrastructure, that means vehicles communicating with roadside access points. If you are doing that sort of communication, you can actually develop these sort of applications, and some of them are curve speed warning. There is a curve ahead. You can actually warn the driver there's a car ahead, and there's a curve ahead. Red light violation warning. As you're driving by and you see there's a green light and there's a red light on the other side, and the infrastructure detects that there's a car coming towards the red light and he's only 20 feet away, driving at 60 miles per hour, so definitely is not going to stop. So actually you can inform the driver approaching the intersection on the green light that there's a driver who is going to violate the red light, so you better be alert. So that sort of applications can be done if you are communicating between vehicle to infrastructure. Then there are other applications like mobility applications. I'm not going to go through this in detail. One of the applications which has not been looked at too much is the road weather applications. That is area we're actually going to look at in this project, that how we develop the road weather applications to increase the safety of drivers by communicating information between vehicles and infrastructure. So here is an example of an application. There are two of them actually there. I'm going to probably discuss this. There is an emergency vehicle coming to an intersection, and the emergency vehicle can send a signal actually to turn the light from red to green so that the car can pass, the emergency vehicle can pass. The second one is safety application, like a car is coming in the wrong side. So this is a ramp which goes out of the highway, and this immediately can be figured out that the car is driving on the wrong side, and this information can be sent to the neighboring vehicles immediately so that this vehicle is aware of the fact that there's a car coming on the wrong side. So this driver can be alerted in real time. How do we do it in real time? That's the question. So I work in the area of networking, so the protocol is called dedicated short-range communications. That is the protocol which has been developed for communication between vehicles in real time. So it's similar to Wi-Fi, but it has some features which are required for real-time applications in vehicles. So it's similar to Wi-Fi. The added advantage is very fast. It's secure, and it has to be reliable. We're not checking email here. We're actually talking about safety, so it has to be very, very reliable. It has to be fast because cars are coming in, cars are leaving, so you have to communicate the message very fast, and there is a imminent danger, you have to communicate very fast, so it has to be extremely fast. So the protocol, actually, the networking protocol sends these messages, which are called basic safety messages, 10 times a second. So these are broadcast 10 times a second, saying that what are the conditions of the cars, what are the parameters in the car. The range is about 2/3 of a mile when you're driving at 200 miles per hour, up to 200 miles per hour. The data rate can be from 6 to 27 megabits per second, so it's pretty high data rate. And the latency is 200 microseconds, so you can get information from one point to another point in 200 microseconds. Its performance is immune to extreme weather conditions because it has been developed specially for vehicles. And eventually, NHTSA will decide whether US will require all car manufacturers to implement this or not, just like they did with airbag, for example. They made it compulsory, saying that all cars must have airbag. So whether they will do it or not, it's not still decided. Yes? In February? Okay. So when does it start? 2018 is compulsory, right? Yeah. Okay, so from 2018 is already made mandatory that light vehicles should have it, right? Okay, so one step is already done. So this project is even more useful now. Thanks, Hazim. So these are some of the messages. So what I'm not going to bore you with all this, but the messages here, the messages you're going to send can have priorities. Unlike Wi-Fi, they have no priorities. Here you can have priorities. So if you are sending a message which is very critical, that will go faster than other messages which are less critical. Like you are sending the information about a turning light, a turning signal. That is not as important as someone who's braking in front, or the car is skidding. So there are 7 levels of priorities, and you can actually, these are all different types of messages, and you can send messages with different priorities. That's one of the things which is quite different from Wi-Fi, which we are all used to. The other thing is the latency is very small. Sending messages, it can be done very fast. So the tasks in this particular project are, we're going to look at what are the DSRC-based equipment. There are 2 types. One is onboard equipment, which is mounted in the vehicle, and then there is roadside equipment. What are the available ones and what we can use to build a test bed to test our applications. We're going to install those in the cars we have in the lab, and we're going to also see how they respond with the inclement weather response vehicles. And we're going to test the equipment for interoperability, whether they work together, because interoperability is a big thing. All cars are not going to manufacture one company. They are going to manufacture a different company. So these protocol must interoperate. Like Wi-Fi is a highly interoperable protocol. You turn on your iPhone, turn on your laptop, everything works. Then we're going to program all this equipment and build the vehicle or ad hoc network connecting the vehicles and the roadside equipment. So basically, we are going to build a test bed to test our application, and then, of course, collect the results and look at the performance. So that's the prototype test bed we have in mind to develop. We'll have a few cars which will be connected by the DSRC. We'll have roadside equipment which will be connected to the cell tower and then to the RV server. So that's a sort of prototype we're going to develop first. So give you some rough ideas. So that's the onboard equipment which has to be mounted in the car, and that is the roadside unit which has to be mounted on the roadside. In this particular case, it's mounted on a tree, I guess, or a pole. I think it's mounted on a pole. So that's sort of equipment we're going to mount and test with. So we already have the roads. We already have some trailers where we're going to mount these. These are already enabled with connections to cell phone towers, and we're going to mount those equipment on these stuff and then test our prototype. So the sort of questions we want to answer, how much time do I have? The sort of questions we're going to answer is what type of surrounding data is most useful to alert the drivers? What sort of data is most useful? Like loss of traction or skidding, or what sort of data is most useful? The application we're going to develop for this sort of safety application, is it scalable? When there are 50 cars, it works. When there are 200 cars, does it work? Is it scalable? Does it scale? How much data can the application handle in real time? Because this has to be in real time. What are the most effective ways to convey weather information? Now, let me remind you again, these vehicle to vehicle, and vehicle to infrastructure, this concept was initially developed for safety applications between cars, like braking and all sorts of stuff. So what are the most effective ways to convey weather information? That is a thrust in this project. What's the best routing protocol to disseminate weather conditions? That's what we're going to disseminate. What's the best routing protocol? How do we route the data from one vehicle to another vehicle, or from one vehicle to all vehicles? What happens when a vehicle cannot disseminate information due to lack of communication? I receive an information, but I lost communication, and I cannot disseminate. I cannot send it to others. What happens in that case? Can the delay-tolerant networking be useful in vehicular networks? This is another concept. Can it be useful? So the sort of expected outcomes is, of course, economic benefits, because there's huge huge losses from fatalities and crashes. greater collaboration with the SPTC consortium members. And of course, once we have some initial results, we'll be in a better position to compete for large funds. So the basic impact we're going to have is reduction in fatalities, injuries, and vehicle crashes, because this is all related to injuries, and all these are related to weather stuff. So we are going to focus only on weather-related safety issues. US DOT already has this project in place, and mostly they are working on safety other than, not mainly the weather. The main thrust is on safety related to braking and that sort of stuff, information communication between vehicles, the current conditions. So we're going to see how the results can be used to demonstrate the US DOT's vision to improve driver safety using this DSRC-based concept, and how to improve the traveler safety by reducing the number and severity of vehicle collisions. So we'll build and test a connected vehicle test bed. We'll try to demonstrate the reduction in vehicle crashes. We'll try to find some numbers, how much it might be, or some idea about how much reduction can be achieved in crashes and fatalities when we use this concept for weather. Answer some of the research questions I just mentioned to reduce the severe weather-related crashes and fatalities. And you'll soon see a car with DSRC. Thank you very much, and if you have any questions, I'll be happy to answer. Sure.
Usually when these issues come up with the privacy in the United States, the privacy issue of the opting in or opting out, is that an issue in this case?
Could you repeat that question?
Yeah, I think the question is there a privacy issue in this particular case that when you are receiving data from other vehicles, that you are identifying the other vehicle? I think privacy is part of the protocol. They have taken into account the privacy as part of the protocol, so these messages are going to be, you're not going to identify these messages. You can actually be private. But whether, I think if the harder question is, if you want to say, I'm going to be on the road, but I'm not going to participate in this, I'm not sure actually what the regulation would be, whether you can opt out or not. I'm not sure. Hazim, do you know the latest standard? Do you know about whether you can opt out when it's mandatory in 2018? You are going to opt out, saying. Okay. So it looks like there's an option to opt out that I'm not going to participate in this.
But the car is going to have, the car by 2018, light vehicles are going to have.
Right. But once you have it and you're on the road, can you opt out saying that I'm not going to connect with others? Yeah, I'm not sure also.
So what will be the range of awareness if another vehicle is following from a fair distance? So will it relay the message to that vehicle, or those should be close enough within certain range?
Okay, what is the question is what is the range of the what is the communication range? I think the communication range is about 2/3 of a mile when you're traveling at 200 miles per hour, up to 200 miles per hour. So you can actually connect with another vehicle 2/3 of a miles away. So here, in this particular case, we are talking about all the cars which are close being connected. So if you want to send a message, it's going to hop from car to car and eventually go as far as it can go. So it's a ad hoc network. They're all connected together. So your message can go quite a distance by hopping from car to car. But between two cars, it should be around maximum 2/3 of a mile. Does that answer your question?
So is there a concern that this will, there is enough distraction while driving? So is that going to add to the things that distract you?
Oh my God, I think I don't know who will answer this.
I'm just,
I'm not sure actually how to answer this question, but at least if you can transmit that information to others that, the car ahead in front is texting, that probably will be, helping us.
I'll try to answer now.
Yeah.
You're looking at the Google car, right? And it's an autonomous car. And so autonomous car, you could really exchange this type of information from a car to a car to tell it to go at what lane and at any given speed and to brake when it needs to be braking, right? So there are technologies right now implemented by multiple cars where you have, if a car hit a brake in front of your car, you have some system that radar or video that will brake your car, avoiding hit of it. So it's this technology that is going to assist you. So instead of, for example, if you're just coming to a stop sign or coming to a car in front of you and you are speeding, and the system is going to prepare the brake, the minute you put a touch on the brake, it's going to apply full force, knowing that if it doesn't, you're going to hit the car behind, in front of you. So there are a lot of technology. It might not take control of your car, but it's going to help you to make the right decision, to make it without really providing you that information. So it's not going to tell you, you know what, if you touch it, I'm going to brake. It's going to brake full power when you touch it. So that type of technology.
Yeah, I hope it doesn't add to the distractions in a negative way. I hope it adds to our driving experience positively.
I think I'll talk a little bit, you know, this is not something new. I mean, US DOT has a program that's been running for the last 3 years where they have 3,000 cars equipped in Michigan, roaming around all the roads in Michigan and trying to test this. Because at one point, this is the result of that, is that they approved enabling technologies and like people to incorporate these type of technologies.
Any other question?
The installation of those roadside-based stations is going to be very costly, right? Can you rely on the communicating through satellites and things like that instead of those stations? Having to communicate information through satellites is very costly.
Okay, the question is, the roadside equipment installation would be very expensive. Instead of doing that, can we use the already installed satellites up in the sky to communicate between the cars? I think from my experience, I will say that the propagation delay from the car to the satellites is about quarter of a second, 250 milliseconds, even the low Earth orbiting satellites. I'm not talking about the geostationary satellites. So the time it will go to the satellite and come back, it might be too late. It's a long propagation delay. So this is a network we're talking about which has to be very, very fast in real time.